today's video we're going to talk about how to read a trace train load report. Before we do that, we're going to just go over the basic formulas you'll need to understand before being able to understand the values in that report. So the main formula will be the total capacity, and that is equal to the sensible heat plus the latent heat. And the sensible heat is basically the heat that is related to the dry bulb temperature. And the dry bulb temperature is basically the temperature that you'll see off a thermometer. The latent heat is related to the amount of moisture in the air, and that's related to the wet bulb temperature. The wet bulb temperature is the temperature that a thermometer would read if it was measuring the moisture in that air. So if you want to think about it, it's kind of like the temperature of your sweat. On some days your sweat will feel cooler than on other days. So on the days that it feels cooler for a given dry bulb temperature, the wet bulb temperature is lower. And if the wet bulb temperature is higher on a given dry bulb temperature, then the sweat would feel warmer on your skin. So the higher the humidity ratio, the higher the wet bulb temperature, and the lower the humidity ratio, the lower the wet bulb temperature for a given dry bulb temperature. Now all this is a lot of information, but once we look at a psychrometric chart, you'll be able to see how all of these relate to each other. And I'm going to go over that later in this video. So the total capacity is in units of BTUs per hour. In other words, MBH, which just is equivalent to 1,000 BTUs per hour. We have another formula. Sensible heat ratio is just a ratio of the sensible heat over the total capacity, which is sensible heat plus latent heat. Okay. Now the sensible heat, there is a formula that can be used to calculate that, and that is 1.08 times the CFM, which is cubic feet per minute. Sensible heat units is in BTUs per hour. The delta T is in units of Fahrenheit. And this 1.08 is basically a number that was calculated by given conditions. So the actual sensible heat equation is equal to specific heat of air over the specific volume times the CFM times a conversion factor of 60 minutes per hour, delta T. So if you look at this formula, the delta T is there, the CFM is there, and this 1.08 is just this value times this value is how that 1.08 was determined. And the specific heat of air and the specific volume, these values actually vary depending on the condition that you're in. So if you look at the table on the right side, okay, the specific heat is given for the temperature of the air. So if you look at this column here, Fahrenheit, you can see that, we're just going to look at the temperatures that are usually within the range of HVAC. Okay, so let's look at around 32 to about, let's say, 80 degrees. If you look towards the right, so you're going to see two columns. One is for isochoric, which stands for constant volume, and isobaric, which stands for constant pressure. So we're looking at this column over here, which is the isobaric column, okay, where it's in constant pressure. because as the temperature of the air is increasing in an HVAC system, it's done at a constant pressure, which is the atmospheric pressure, okay, which is at 14.5 psi. Now, if the air was in a sealed container and we were heating the air within that sealed container, then it would be a constant volume condition. But in HVAC, it's not at a constant volume. It's not completely sealed because buildings are usually have cracks and leaks that allow the air to escape. Right? It's not a 100% sealed container. So we're looking at this column here, the isobaric specific heat. And if you look, these are the units that we're going to be using. This column here. Oh, sorry, not that one. It's actually this column here. And these are the units we're going to be using right here. So you'll see that it's actually BTUs over the pounds times the Fahrenheit. So specific heat basically means how much heat is required to move 1 pound of that air 1 degree Fahrenheit. Or if you look at it the other way, it's if you take out how much BTU is taken out of 1 pound of air to move it 1 degree Fahrenheit less. That's what the specific heat represents. Specific volume is actually in units of cubic feet over pounds. So it's just the inverse of density, which is pounds over cubic feet. And the specific heat of units of air is in units of BTUs over a pound per Fahrenheit, which we just talked about. And the CFM is in cubic feet per minute. Okay, and delta T is in units of F. So we're going to start inputting data into this formula. So we have specific heat. Okay, so we have this number here for the specific heat of air. Specific volume, we're going to have to look at the next chart here, which is the psych chart. So, okay, in this psych chart, I'm going to just quickly kind of go over what these numbers represent. So here on the bottom here is the dry bulb temperature of the air. And if you look here, the wet bulb temperature, these are all indicated right here. This is the wet bulb temperature, and they actually move along a diagonal line, such as this right here. This is the wet bulb temperature. And this is the relative humidity, which follows these lines here. Okay, and the 50% relative humidity is this line here. If you look on this side, the humidity ratio is in grains of moisture per pound of dry air, and those are represented by these numbers here. So we're gonna use this table to get the specific volume, which is this line here. And we're going to get the specific volume of air at 60-degree dry bulb temperature and around 50% relative humidity. So we're right around this area here. And if you look at the specific volume, it's between 13 and 13.5. So let's say it's somewhere in the middle. So let's say it's 13.25. So if we use 13.25, and the specific heat of air is approximately 0.24. We multiply that by the 60 minutes per hour, and if you calculate that number there, it's going to be equivalent to 0.087, which is approximately 1.08, and that is how they got this unit here of 1.08. So that's basically how that unit came about. So when you use this formula, sensible heat, this is dependent upon a condition where it's about 60 degrees Fahrenheit and about 50% relative humidity. So when you look at the load calcs, sometimes the values will be slightly different from just using this formula, and that is due to the fact that the air is not exactly at that condition of 60 degrees and 50% relative humidity. But the number is close enough that this formula is a good approximation of the sensible heat. Moving down, we have a formula for latent heat, which is this here. And again, this formula is also based on certain conditions, because once you have CFM involved in the equation, the CFM will change because the specific volume changes depending on what temperature the air is at. So again, this is also an estimate of the latent heat. This is the latent heat formula. To calculate it, it's 4,840 times CFM times delta W, which is just the humidity ratio. Alright, which is in units of pounds of water over pounds of air. And if you need to do a conversion, if you're giving grains of moisture, it's just 7,000 grains of moisture per pound of water. So you can use that conversion to convert 2 pounds of water over pounds of air in order to use it within this formula here. And this 4840 again is just a number based on certain conditions of the air, and because that condition could vary slightly because the cubic feet or the specific volume of the air can vary depending on where you are on that psychrometric chart, based on dry bulb temperature and the relative humidity. So this value is based on a specific condition. So sometimes if you look at the load calcs, the numbers might be slightly different for the latent heat based on the values that you might get using this formula, just because it might be at a different condition. But these formulas give you a very good estimate of it, which is close enough, and this is the reason why these formulas would be sufficient at giving you a good estimate of the latent heat. And the total capacity formula is the sum of the latent plus sensible heat, or you can just multiply the CFM by 4.5 times the change in H, which is just the enthalpy. Okay, so we're going to look at a systems report from Train Trace. And in this report, I'm just going to go over the different sections of this report, starting from the upper left corner, which is the cooling coil peak. So this section here is the cooling part. If you look at the top, the peak time is calculated at being the month and the hour. So it's the month of 8, which is August, and it happens at the hours of 15. So 15 would convert to 3 p.m. So at 0 would be 12 a.m., at 1 would be 1 a.m., and 15 is equivalent to 3 p.m. And at that time, the outside air dry bulb is 88, the wet bulb is 76, and the humidity ratio is 115. Now if you look at the column on the bottom, it basically breaks it down into two sections. One is the envelope load and the other is internal loads. The envelope load will just give you the heat transfer across any part of the envelope, such as the skylight, the roof, the walls, the glass, as well as all these other items in that list. Now if you look at the columns, one is it says space and one says plenum. When we put in the load calcs, we define a plenum space. So that space that we defined would have some sort of sensible and latent heat, and that's why you see these two columns here. So the space is anything below the plenum, and whatever's in the plenum would be calculated separately. So if you look, you can see there's a small portion of, let's say, the wall conduction. A small portion of the wall conduction is in the space, and a portion of that wall conduction is in the plenum, because the wall is shared between the space and the plenum. If you remember, if this is the floor, this will be the plenum. So if this whole section is the wall, a certain portion of that heat would be in the plenum and a certain portion would be in the floor. So you see a breakdown of that for the wall conduction. Now for the roof conduction, you see 100% of that roof conduction is occurring in the plenum, and that's because the plenum is taking all of the heat from the roof, and that heat doesn't actually go into the space directly. So that's how the columns are broken down, and you can see the net total would just be the combination of the space column and the plenum. So if you just add these values up here, for instance, you'll get the total here, and it gives you a percentage based on the subtotal here. And for the internal load, the same thing. You'll see there's a subtotal here of 46 and a subtotal here of 55. So if you add those two numbers up, you get 101, and it's 101 just because you have this -1 here, which now gives you 100%. So out of these values below, you'll see some of these are giving you certain values. So this is adding heat. A positive value means you're adding heat, and a negative value means the heat is going out. So the ceiling load, it basically cancels out. This is exhaust heat. So you can see some heat is being removed from being exhausted out of the space, and the total is right here, 23,520. So if you convert that to MBH, it's 23.5, which is how this number got here for the total capacity for cooling.